In today's video, we will be dealing with the case of finding the center of mass of a thin plate, no objects on it, just an irregularly shaped, even thinness plate that we're trying to balance somehow. Now, in particular, let's suppose that the plate has a shape of this nature. It can be bounded by a vertical line on the left, x equals a vertical line on the right, x equals b, some function of x at the top, let's call it f of x, and some function of x on the bottom, let's call it g of x. Now, having the restriction that the sides have to be straight does limit the applicability of this theorem, but we won't be able to treat more complicated functions than this until you get to multivariable calculus, probably. At least Calc 3, but probably not until you reach Calc 4. If you want to find the mass of this plate, then we can start by finding the area of the plate and then multiplying the area by the plate's density, which I'm calling rho for short. The mass of the plate is equal to m for short, I will call it rho, the density, times the area, and we can recall that the area between two functions can be found by adding up the difference between their y values, f of x minus g of x, with respect to x. Then the question is, what is the center of mass? Now, this can be a little bit difficult to justify at this point, and we won't take time to go through how this formula is derived. But for right now, we're just going to state it. If you want to find the center of mass, that will also be given by a ratio, just like in the finite number of objects case. A ratio of a quantity which I will call m sub y, with a quantity that I will call lowercase m, and this is the same m as we gave in the previous example. Okay, so let us come up with an expression for m sub y. M sub y is equal once again to the density of an integral from a to b of x times f of x minus g of x dx. So in other words, if you would like to find the x-coordinate of the center of mass, in other words, you can take x bar, and that will be equal to the integral from a to b of x times f of x minus g of x. And you can divide that by the integral from a to b of the same thing, except without x in the integrand. Notice that the row that appears in m sub y and the row that appears in m will always cancel each other out if you put them in a ratio like this. So my mnemonic here, to help me to remember what is going on, is that for x bar, the ratio of these two integrals, x bar will have an extra x in the numerator of the integrand, an extra x to find x bar. That's how I remember it. Now, to find the y-coordinate of the integrand, to find y bar, this is often called the product of m sub x and lowercase m, where m sub x is equal to the following integral, is equal to rho times the integral from a to b of 1/2 f of x squared, take away g of x squared. Integrate that with respect to x. So in other words, if you want to calculate y bar, you can do that by integrating from a to b f of x squared minus g of x squared with respect to x, and you can divide that by 2 from this 1/2 of the integral from a to b, f of x minus g of x. And the way that I remember this is that x bar had an extra copy of x in its numerator. We had x times f of x and x times g of x in its numerator. Whereas y bar has an extra copy of the outputs in its numerator. Not x times f of x, not x times g of x, but f of x times f of x, giving you f of x squared. G of x times g of x, giving you g of x squared. So x bar has an extra input, y bar has an extra output in the numerator. Is a mnemonic that sometimes I will use to help me. So let's go ahead and let's apply that problem to the following exercise. Consider a plate shaped like the finite region bounded by f of x equals square root of x and g of x equals x. So f of x equals square root of x looks like this. G of x equals x, straight line. And the area between them is bounded by x equals 1 and x equals 0. Assuming that the plate has a density of rho equals 0.5 units, find the total mass of the plate and find its center of mass. Now the total mass of the plate can be found by taking that density of 1/2 units and multiplying it by the area of the region trapped between f of x and g of x. So the integral from 1 to 0 of top function minus bottom function with respect to x. Using power rule as always, we get x to the power 3/2 times 2/3 x squared over 2, and we'll be evaluating that from 0 to 1. And as usual, plugging in 0 to this sum of power functions will give us 0 as a result. So I'll have 0.5, plug in 1, 2/3 minus 1/2. Now distribute that half, we get 1/3 minus 1/4. And so the mass of this object is equal to 1/12. 1/12 is the object's mass. So now let's go ahead and let's calculate m sub y, and let's calculate m sub x, and let's find out what the centers of mass would be. M sub y is equal to the density 0.5 times the integral from 0 to 1. Now m sub y is used to find x bar, and x bar is the integral that has the extra x. So I need to integrate this function. 0.5, integrate from 0 to 1, x to the 3/2 minus x squared after distributing that x through, 0.5, and then let's take an antiderivative, x to the 5/2 times 2/5, x cubed over 3, evaluated from 0 to 1, and then plugging in 1, since 0 doesn't contribute here, 0.5, 1 goes in, 2/5 minus 1/3. I suppose that this is 0.5, 1 over 15, so I suppose that this is 1/30th for the value of m sub y. And similarly, we can find the value of m sub x. And recall that m sub x was used to find y. And so the formula for m sub x used to find y will have extra outputs f of x squared and g of x squared. So this will be rho, the density, 0.5, integral from 0 to 1 of 1/2 times the quantity f of x squared minus g of x squared. So that will be equal to 1/4 integral from 0 to 1 of x minus x squared. Finding our favorite antiderivative gives me 1 over 4, x squared over 2, take away x cubed over 3, evaluated from 0 to 1. And so, finally, plugging in 1, we get 1/4, 1/2, take away 1/3, 1/4 times 1/6, 1 over 24. So now, in order to actually find the centers of mass, I just need to appropriately assemble the values of m sub y, the values of m sub x, and the value of lowercase m. Lowercase m is 1/12. I'm just going to make a note of that. X bar is equal to my over lowercase m. Now, my was equal to 1/30. Divided by 1/12, multiplied by the reciprocal, we get 12 over 30. Y bar is equal to mx over m. So 1 over 24 divided by 1 over 12, or 12 over 24. Now you can reduce these if you are so inclined. You can convert them to decimals. But with this number, we have obtained the final answer. If you would like to know the total mass of this plate, take the area of the plate, multiply it by the density, and you'll get that the result is 1 over 12. If you want to know where you should position your hand in order to balance this plate on your hand, here are the coordinates. Put your hand at x equals 12 over 30, and put your hand at y equals 12 over 24 to find the balancing point for this region.